Maybe you can make the full screen presentation. In principle, in principle, it's okay. Please proceed.
Okay. Can I start, please?
Yes, please.
Okay. Hello, everyone, and welcome to my presentation. I will talk about three short topic, and I try to finish early so that on time I can finish on my time. I will talk about some set of new solution of metrics and that are in the presence of a scalar field. My talk is about, at first, a three-parameter matrix in the presence of a scalar field, rotating three-parameter matrix, and charge three-parameter matrix. You can find more detail about this talk in these papers on arXiv. A simple Einstein-Hilbert action can be written as follow. As you see, we have a term that is a pure scalar field that only depend on R, and equation of motion are as follows. As you see, the Ricci tensor can be written as derivative of these functions, phi, that phi is a scalar field. This set of equation was solved many years ago by Yanis, Newman, Wincor, and Fisher, and it's a very famous solution called JNW or FJNW metric. This metric has two parameters. One is related to mass. This M is correspond to mass. It's actually proportional to physical mass of such object if it exists in our universe. Gamma is another parameter, and we have two parameters of this metric. This is the solution of this R mu nu equal to d mu phi d nu phi. And this solution is well known. And for a long time, we had only this solution for this set of equations. No other solution was known. This solution has two singularity, one at R equal to 0, the other one at R equal to 2m. These singularities are naked. The 2m is a naked singularity, and we have actually a naked singularity. There is a lot of papers about this JNW metric and possible observational effect that this kind of object might have in our universe. A lot of papers exist. One question that people were thinking about it was a rotating solution of this JNW metric. How can we find a rotating solution for JNW metric? One standard method is Yanis-Newman algorithm. However, Yanis-Newman algorithm doesn't work for this metric, and we cannot use Yanis-Newman method to find a rotating form of this metric. It should be noted that some papers use the Yanis-Newman metric and wrote wrong solution of rotating form of this metric. The solution that can be found by using Yanis-Newman algorithm actually does not satisfy the second equation that we see here, R mu nu equal to derivatives of phi. This This equation has if you see R mu nu or Ricci tensor, all diagonal elements are zero except one, which is RRR. The RR component of this Ricci tensor should not be zero. Actually, we found recently a generalized three-parameter metric that is a generalized form of J and W metric. This metric, as you see, has three parameters. One is M, and two others are gamma and mu, or gamma and mu, because these three, gamma, mu, and mu, are related by a simple equation and are not independent. Therefore, we have only three parameters in this metric. One parameter more than the Yanis-Newman-Winkour metric. This function f and k are, as you see, as usual, and we can find these functions exactly by a simple method, which is a perturbative method, by using a perturbation method up to first order in M, and using R theta equal to 0, we find beta is equal to 1 minus gamma. Beta is in here in this metric. And using R theta, we find mu plus nu is equal to beta, where mu plus nu is 1 minus gamma as beta. You see, this is a relation between these three parameters. Therefore, we have only two independent parameters. The other equation, R theta equal to 0, gives us the unknown function n of theta, which is sine of theta. The equation of Ricci tensor gives us exact solution for a scalar field, as you can see. This is our scalar field in this solution. This solution is very simple and completely very similar to the gamma metric. Gamma metric is defined by a set of parameters, as if we choose nu equal to 1 minus gamma 2 and mu equal to gamma to power of 2 minus gamma and phi equal to 0. You see that phi, if this coefficient nu be equal to 1 minus gamma 2, phi becomes 0. And at different values of these parameters, this metric, this three-parameter metric, reduces to J and W metric and gamma metric that are well known, and many papers are written for these two types of metrics. However, this new form of metric that we found has in a special limit reduces to these two types of old known metrics. And we have found a lot of other metrics if we choose mu and nu for other values, and we can find many new solutions that are all related to gamma metric and very similar to gamma metric. Gamma metric is a metric with a quadrupole moment, is a mass distribution with quadrupole moment, and is a candidate for the center of Milky Way. It could be a candidate for the center of Milky Way. And this set of metrics that we have found all could be and other candidates for center of our Milky Way. It depends on choice of these parameters, mu and mu. And this is why this set of metrics might be significant in observational physics. This is the four-dimensional form of gamma metric. We can write it in isotropic form. that might be helpful for generalizing this metric to higher dimensions, that you can see this metric in isotropic form. We can find Ricci a scalar of this metric because we have a scalar field. The Ricci scalar is not zero, and the singularity points can easily be found by looking at R. Singularities are at 0 to m, and m times 1 plus minus cosine of theta. These are new singularities that we can see in this metric. These singularities are exactly similar to the singularities in the gamma metric. The difference is that in gamma metric, Ricci scalar is 0, but here Ricci scalar is not 0. If we put nu in numerator here, nu equal to 1 minus gamma to the power of 2, then this Ricci scalar becomes 0, and we have, again, gamma metric. Gamma metric is a special case of these three-parameter metrics. It's interesting that we can generalize this type of metric to 5-dimensional case in the Boyer-Lindquist coordinate, in similar to Boyer-Lindquist coordinate that is written in here. But there is something strange with this metric. It's completely hard to find it in other angular coordinates, in 3-dimension angular coordinates that is different. We can write them in different form rather than this form. And there is another strange thing that we cannot generalize this 5-dimensional solution to 6 or higher dimension, except at very trivial line elements that are related to this spherical part of metric. This is an open solution that we don't know how to solve this solution. It's very hard solution, actually, that this kind of coordinates cannot be generalized to 6 or higher dimensions. This 5-dimensional metric also can be reduced to JNW metric in 5-dimension and 5-dimensional gamma metric, that you can find in this paper more details about this reduction. Again, we can find Ricci scalar for this 5-dimensional metric that gives us very simply all singular points. Here, we don't need to use Kereshman scalar that has a very large form of functions. However, Ricci scalar is very simple, and we can find all singularities. The isotropic form can be written easily as follows, as you see. And for higher dimensions, we don't have a solution in spherical coordinates, in normal spherical coordinates or Boyer-Lindquist-like coordinates. The only solution we found in higher dimension has a kind of toroidal coordinates, as you see here, and flat coordinates that we can write psi and phi, psi, theta as follows, as you see. As I said, it's an open question that how to write this metric in Boyer-Lindquist form of coordinates. This solution that we found, 3-parameter metric, is exactly very similar to the gamma metric. As you know, gamma metric has exact rotating solution. This was our key point, that we found rotating solutions for this metric, for the 3-parameter metric. To find rotating solution, we can use Weil metric, as you can see, which is more similar to cylindrical coordinate, and then write it in X and Y coordinates when rho is equal to X to the power 2 with this coordinate transformation. We can write in X and Y coordinates, this metric, it is very simple, and then use Ernst method and find the following equations that follows from Einstein equations. RTT and RTphi gives us these two equations here, and the other Rxx, Ryy, and Rxy gives us these equations. Here, this part of dot, dot, dot are exactly similar to what we have in rotating solution of gamma metric. However, here we have a scalar field, and this part is more than what we see in gamma metric. The other part in here also is the same, and dot, dot, dot is the same as what we have in gamma metric. It is interesting that we can do the second derivative of these two equations, and it gives us a simple solution for phi, the scalar field in the rotating case. That is as follows that you see. If we use the Ernst equations and find this E that equal to Laplace function base plus I times U, that is Ernst potential, we can show easily that the following E and other definitions satisfies all equations of the Ernst equation. These equations that you can see in here. So if we use the following definitions, this definition with the other D, H, alpha, and Q, we can write a rotating form of this metric. The rotating form of metric can be written as you see in this page. However, it has a very long mathematical formula for each values of the parameter, except one exceptional case that I will explain in the next page. A scalar field phi can be written for the rotating metric as you see. The only difference with non-rotating metric is these two terms that in m to the power 2 minus a2. And here exactly Ricci tensor can be calculated and show that Ricci tensor equals to dr phi, dr phi. And the other components of Ricci tensor are all 0. In this solution, of course, this should be done by computer and using Mathematica or Maple softwares. And by these softwares, we can show that the Ricci tensor is exactly given by these metrics. We have different limits. We can find rotating gamma metric. We can find Bogosh-Galistov metric at one special value of the parameters. If we choose gamma equal to 1 and mu equal to minus mu, we have a very interesting form of rotating metric. The other values can also be studied easily. The quasi-normal modes of this metric can also be studied. Quasi-normal, because in this metric we cannot separate variables for the wave equations. Therefore, we have to use a method of quasi-normal modes that don't need to separation of variables. This method called light ring method that was introduced by Ferrari and Mashun many years ago. We use this light ring method to study quasi-normal modes of this metric. Quasi-normal modes in the light ring method can be easily found. Of course, other people can use exact numerical study for these quasi-normal modes. We haven't done it yet, but it can be done in the near future. And for different values of parameters, we can study quasi-normal modes. Quasi-normal modes can be found for rotating J and W metric as follows. for other value, for example, gamma equal to 0 and gamma equal to 1 in 0 is not correct, gamma equal to 1 and mu equal to minus nu. It is as follows, and we can compare these quasi-normal modes, and the imaginary parts may give us a stability of these metrics. We can see easily that quasi-normal modes of J and W and quasi-normal modes of the other special value, that is Bogosh-Galistov metric, gives us some different parts that we can say that J and W metric is is less stable than BG metric. We can find a stability of these metrics by using quasi-normal modes. We haven't done too much work on this topic, and it can be done in the future by other people, or we also do some more calculation using quasi-normal modes. Recently, we have found charge form of these metrics that is not too hard to find. Of course, this is charge form of non-rotating metrics. We used, again, Ernst equations and used the Harrison transformation. By using Harrison transformation, we can find charge form of these metrics. Ernst potential can be defined as you can see here, and the AT and A phi are vector potentials that we can calculate easily. The Harrison transformation can be done very easily here, and we find charge form of this metric. We start with this form of metric here, and then our metric, our original metric, is written as follows. Then we can use Harrison transformation. By Harrison transformation, we can choose lapse function equal to E, the Ernst potential. Ernst potential phi is equal to 0 in Ernst equation, and E to the power 2 eta in the new coordinate. You can see here E to the power 2 eta in this new coordinate can be written as follows. And then a simple Harrison transformation give us charge metric. The charge metric can be found, and the lapse function is given in here. And the vector potential is written in here. We can also do some transformation to deform it to the more known solution, similar to Reissner-Nordstrom solution. And this is the final solution that we found for charge metric. That you can see is very similar to Reissner-Nordstrom solution. However, if we put gamma equal to 1, we find exactly a metric that is very similar to Reissner-Nordstrom solution. As you see in here, the only difference is this part that is related to the scalar field. And the other parts are exactly similar to the Reissner-Nordstrom solution. This is very interesting that in this case, we have found a very simple solution at gamma equal to 1, and only one other parameter nu gives us this new solution. The J and W metric is not most general solution for the Einstein-Hilbert action in the presence of a scalar field. We derived a more general three-parameter solution with quadrupole moments. It should be noted that Yanis-Newman method does not work for deriving the rotating J and W metric. We obtain a class of rotating metric using the Ernst method that has a correct, that satisfy correct equation of motion. By using the Ernst equations, we can find charge form of the metric. Of course, a lot of new calculation can be done for these new three-parameter rotating metrics in the future. And thank you for your attention. I hope that this short talk could be useful for some of you that might be interested to work on this type of metrics. Thank you very much.
Thank you very much, Professor. So questions from Zoom first. Questions from audience? Okay. I'll ask one question. Could you please scroll back to one of the first slides where you show the non-rotating variant of the matrix?
Could you
The very beginning.
please? Could you say it again, please? What?
Yes. Maybe even earlier.
Okay.
Okay.
Okay. In here is here.
Maybe the next slide with the expression for the scalar field.
Okay. In here.
Yeah. Is there a simple qualitative explanation why scalar fields, while the scalar field remains spherically symmetric in presence of theta dependence of the metric itself?
Oh yes, actually, this as I said, if we put this non-spherically symmetric metric, it's metric that has quadrupole. This if you see this metric, you can see two different values for this nu. If nu is greater than 0, we have a correlate distribution of matter. If nu is less than 0, we have oblate distribution of matter. This is very important. This nu shows the oblate or spheroid, oblate or correlate distribution of matters. This parameter nu. This scalar field vanishes for the gamma metric. In the gamma metric, we don't have a scalar field. However, we have these quadrupole moments for the metric, for this metric that you see. In here, what we can show is that the Ricci tensor exactly satisfies this equation, and all other components of the Ricci tensor are equal to 0. Therefore, the only thing that we can say about the Einstein equation is R, R, R. This part of Einstein equation depends on phi. You should think about gamma metric. Gamma metric has quadrupole, but however, there is no scalar field. Here we have only one scalar field with that depends on R, and the only non-zero and non-vanishing Ricci tensor is RR. All other R vanishes. I can't say anything more about this because phi is not exactly the source for quadrupole moment. I can't say something such as that phi is a source for quadrupole moments. As I said, gamma metric also has quadrupole moments, and coefficient of metric depend on theta. What phi does for us is just to change these parameters mu and nu. And I cannot say more about this to you. I don't know how to explain that why phi is not depend on theta also. If phi dependent on theta, then our Ricci tensor must have other coordinates not equal to 0, other parts not equal to 0. If you see this equation, if phi be dependent on theta, then I have to write another d theta phi here, dr d theta phi here and here. These four coordinates are all can be written, and r it should be equal to all of these. In this solution that we found, we don't have the other part, and the others are all equal to 0. However, if we find an accelerating metric that is a generalized form of this solution that we found, that we publish it later, we have all these coordinates non-zero. R theta theta, and R theta R. That's all I can say about this solution.
Thank you. More questions? Okay, we are slightly behind the timetable, so let's proceed to discussion. We have 45 minutes left. Now I pass the virtual microphone to our discussion leader, Professor Pokrovsky.
Thank you very much.
Thank you.